Hello everyone. Today we're going to talk about population ecology. So we're moving into that last section of the course, the ecology section. We'll start talking about how things interact, all the different ways that organisms rely on each other and fight against each other and eat each other and all kinds of good stuff. So we're going to talk about general populations though first, to kind of start off with how populations kind of interact with each other and how they kind of shift over time and ways that these populations grow and change as far as ecology goes. So with population ecology, we got to define what a population is. So a population is a group of individuals of the same species in a given area. So they're all the organisms in the same species in a general area. So we could say like all the squirrels in Fredericksburg, okay? So that would be a population. And the demographics are the characteristics of that population. So what are the characteristics, what are the traits of all those different organisms within that group? So what type of possibilities are out there? And the demographics of a given population is the starting point to understanding the ecology of an area. So when you look at all the different types and all the different possibilities of that population, you can kind of start getting an idea of what's happening in that area, where that population might be going as far as how it's changing and how it's adapting to the ecology and the organisms around it, and how all of these things are starting to interact. Demographics is that population, is the population size, is the number of individuals. So when we talk about population size as part of those demographics, it's the number of individuals that potentially contribute to the gene pool. So it's all the ones that are capable of breeding. So if something's sterile, then it's no longer in that population size group. But anything that is capable of contributing to the gene pool at some point in time is included in the population size. Age structure is the number of individuals in several different age categories. So typically you have your very young, your kind of teenage years, your reproductive years, and then your post-reproductive years. And reproductive base refers to all individuals that are currently or will be reproductively active. So that's everything before that post-reproductive age time. So everything from babies all the way up to, typically, I guess if you look at humans, 50s, 60s, kind of an idea. So they're capable of at least reproducing and adding and changing in that gene pool. So population density refers to the number of individuals in some specified area, or the volume of the habitat. So it's how many organisms you have in a given section. So a lot of times humans, we refer to population density, especially when we start talking about cities or rural areas and comparing the two. So you want to look at how closely packed in people are, like when you start talking about Tokyo and how there's like thousands of people per square or millions of people per square mile, or you start looking at South Dakota where there's like 3 people per square mile. That's the idea of population density. Population distribution is the pattern in which those organisms are spread within that range. So when you're talking about 3 people per square mile, are they evenly dispersed? Or are they clumped up? Are the 3 people all live in one house? Kind of idea. So how is that population distributed within that entire group? Are they spread out evenly, or are they kind of in groups in random areas, or are they just completely random all throughout that entire area? So here's a nice little diagram. Shows people per square mile. Shows how we're grouping. So we are typically, as humans, tend to group in clumps. So you'll have large clumps in certain locations, right, where the population density is much higher than those areas which have very low population densities. So with population dispersion, you have interspecific interactions influence each population's density and dispersion within a habitat. So how they interact within that species. So clumping is the most common for animals. Resources are rarely uniform through a habitat, so you get clumping of organisms around those resources, like watering holes, things like that. You got social groups, so with families, that'll start causing clumping, families and herds and things like that. And then you have your dispersal of offspring. So how do they get rid of the offspring? So if you got them spread out, if the offspring are able to roam very easily, then you might get more of a dispersed group. If they're not, thinking about some types of plants, then you're going to have clumping just because of the offspring can't really travel very far from the parent. So you get this clumping of them around the original parent in that area. When counting a population, you come into lots of issues. Right? You can actually do a full count, which involves counting every single one person or every single organism within that population. That is exhausting. Things move around. It makes it very difficult. And so this is typically not used unless you're doing like trees or something large that doesn't move. Then this really isn't practical. And so they use sampling. Sampling involves dividing up an area into quadrants, into little sections, and extrapolating what the population is by doing samples in those little quadrants. You can do capture and recapture. And so with capture and recapture, you capture a certain set of organisms, you tag them, you release them, you let them go around and spread out again, and then you recapture some of those organisms, and you look at the percentage of your recapture, how many of them have the tags that you have. So let's say you tag 1,000 birds, you release all the birds, and you let them go for a month, and you come back and you capture another 1,000 birds, and you look and see what percentage of those 1,000 birds that you captured have tags, and that gives you an idea of, well, that 1,000, if it's like 10% of the 1,000 have tags, then you know the 1,000 that you had is 10% of the entire population, and so you can extrapolate and see what the total population would be. So that's a general idea. Obviously, there's lots of problems. It's not exact, but it can give you kind of an idea of what's happening. With population size, you got immigration and emigration that end up affecting this. So immigration, things coming into the population; emigration, organisms leaving the population. You got migration, which can change this, especially with birds, causes a big problem because you got birds migrating up and down the coast and migrating from cold areas to warm areas, and then back to the cooler areas in the summertime. And so all of this can make it very difficult when trying to count a population. This is why with a lot of birds, especially migratory birds, we really, they say that lots of them are endangered, but they can't provide a whole lot of data because it's very difficult to gather. Hard data anyways. Zero population growth assumes that immigration is equal to immigration and therefore doesn't play a role in population size. That's one of the things that most groups end up kind of assuming, is that you don't have the organisms abandoning this particular area and immigrating out, or you don't have this giant influx of organisms coming in from another group. And they expect that some of them will leave, but some of them will come in, and it kind of helps, kind of balances each other out. And so it doesn't affect the general overall population size a whole lot. When calculating the population size, you got to figure out the birth rate and the death rate to figure out your net reproduction per individual. All right, so birth rate is how many babies you make per year. Death rate is how many organisms die per year. And so these figure out in combination to produce for the net reproduction per individual per unit. So you figure out how many of them live, how many of them die per year, and that helps you total how the population is growing, or if it's not. So you got a nice little diagram here of how the population goes. So you got China, right red up there. You got India, the orange, and then you got the U.S. and Europe. And so you can look in the 1960s, late 50s or early 60s into the 70s, China had a massive explosion of the population right here, and China, or in India, had a pretty big increase also. But China had this massive explosion, and ever since then, all the populations have pretty much been decreasing overall, and now are kind of steadying out. We actually had a major decrease in the 95 to 2000 area in kind of bottomed out for Europe, and they're slowly starting to come back up. But you can see all these populations kind of leveling off here as far as their overall population. And this is, you'll notice now that they're leveling off actually below the 1.0 line. And so that 1.0 line is when the population is actually increasing. So the population of the Earth is actually overall slightly below the holding margin. So that means the populations will slowly start to decrease. And so over time, our population now is actually, as a general, at least as looking at these major groups here, is actually decreasing now. So, which is a good thing, right? If you're above the 1.0 line, that means that our population is always increasing. If you're below this 1.0 line, that means it's decreasing. And so we're slightly below. We're 0.9. We're not a whole lot below, but we're slightly below. And so that means our population now is kind of starting to level off and is not increasing as fast as it was. And so over time, the population will slowly start to decrease. Not massively, not enough necessarily affect all of the things that we're doing to the planet, but at least it's not exploding in the population. So population growth is that net population growth rate times the population number. So our growth rate right now is 0.9. Times the population number is our general population growth, and so that's a negative, or that's a lower than what the population than what needs to be to maintain the population. So our rate is decreasing. You can have exponential growth. So as long as the birth rates exceed the death rates, that's where it's above that 1.0 line. There will be exponential growth. We don't have that right now. We did at one point in time. We had it significantly, especially in the 60s and 70s. But as of now, our rate is lower, and so we don't have the exponential growth. But before then, all the time before then, we definitely did. And so that's how we've gotten to 7 billion people or more than that even on the Earth today. So doubling time is the amount of time it takes for a population to double. Sorry, so going from 5 billion to 10 billion to 20 billion to 40 billion, that kind of idea, and see how fast the population increases. And it depends on the biotic potential, how the organisms grow, how they reproduce, and that kind of thing. All right, so these are important things that you need to know. You're going to see a chart like this, and so you're going to need to make sure that you kind of understand a couple of these different terms. You got the population size here on the left of the chart, time on the bottom. And what this is showing is how the population increases over time. So you have, when you're starting off with a low population, it takes a while for it to increase, but you're going to continue to get this exponential growth where it's above that 1.0. Right? And the maximum growth, like what hit China in the 1960s, is somewhere around in here. And then it starts to, and then it increases, and then we start hitting something called carrying capacity. What carrying capacity is the limit of that environment can support. So it's a number of organisms that particular environment is capable of supporting as far as whatever resource. There's something called a limiting factor. And that limiting factor is that resource that holds back or restricts that population. And so whatever that limiting factor is, if it's in most places it's food, it could be water, it could be space, it just depends. And so that there's some kind of limiting factor that will hold back a population whenever you have this carrying capacity. So whatever that limiting factor is, it sets that carrying capacity. This is how many that environment can hold. If you go above that number, you don't have enough resources to keep everybody alive, so some people are going to die. If you are down below this number, that means you still got some resources, and so that population will still increase until it reaches up to that carrying capacity. And then it slowly starts to level off. Sometimes it'll go above, some organisms have to die, sometimes it'll go below, leaving a little space for it to grow again, but it'll kind of waver and go right around this carrying capacity of that environment as long as that limiting factor still stays stable. So you can have density-dependent limiting factors and density-independent limiting factors. And this is kind of an interesting idea that we need to talk about. So that can be a little difficult for some people to understand. So density-dependent factors are things that make a difference in how dense your population is. So things like food, right? So if you start increasing the density of the population, you're going to start running out of food because you only have so much space for that food to grow. Space is, by definition, a limiting factor for density dependent because you only have so many places you can live in an area. Tokyo is running into that problem. Nutrients goes along with food. Waste, right? Trying to get rid of your waste. If you have so many people in an area, that waste builds up also and can limit the ability of that population. So carrying capacity is the maximum number of individuals that a given environment can sustain indefinitely. So it's the number of organisms that that environment, based on that limiting factor, can actually hold. And so you have this logistical growth or logarithmic where it increases and then slowly decreases. We get that nice little curve that we were looking at. And we have our density independent and density dependent controls. Right, so density dependent controls are things that rely on that density. So these are things that hold that population back besides just that limiting factor. And these are things like predators, parasites, pathogens. All of these will impact the population of a group of organisms as their density increases. So as you get more organisms in an area, predators will find it easier to get food, and so that'll help keep the population down a little bit. Parasites and pathogens, diseases will spread a lot easier when you get a high density. Right? When you're at low density, you don't come in contact with each other as much, and so it's much more difficult to pass along diseases. Once you start getting to a certain point and everybody starts bumping into everybody else, you start getting an increase in that waste, and so diseases and parasites start spreading like crazy, and that drops down the population also. And so you have these density-dependent controls that will affect that population and keep it down also, including and not really impacted by the limiting factor, but just as what happens as the population increases. Density-independent controls are things that affect the population. It really doesn't matter how many you have. Things like freezes, deforestation, comets, volcanoes, things like that are going to affect a population and affect that area no matter if there's 1 million people or if there's 2 people. It'll still impact that area. And so they don't matter how many that there are, it just matters if there are some in that area or not. And so these things will affect the population no matter what. These things affect the population more as the density increases. All right, life history patterns. All individuals in a population are not necessarily identical, so therefore you're going to have some that do really well and some that don't do so well. So life history patterns are a set of adaptations that influence survival, fertility, and age at first reproduction. So they're kind of the general patterns of the population on when they reproduce, how they grow, how long they live, that kind of thing. So these will cause individuals to act differently within their environment at different times in their life. So as you're growing and getting up to maturity, you react a lot differently than when you actually get to maturity. And then you react a lot differently when you stop necessarily reproducing. And so your expectations and how you interact with your environment makes a big difference. So this is a nice little diagram that shows life expectancy of birth for when they were born to how they'll live. So people that were born in the 1950s, at that point in time, their life expectancy was for males, about 67, and females about 71. For people born my age, 1980 to 82, right, my life expectancy is a little bit above 70 or right at 70, and my wife's expectancy is about 76, 77. And then for people born in the 2000s, you're up here at 76, 77, and up into the 80s for life expectancy. And so that's a huge increase. I mean, if you look at going from 67 to 78, you're talking about almost a 10-year difference in males just by being born later due to our medical advances and all that kind of stuff. So pretty crazy. So life tables give data on the cohorts. They tell about the groups. They tell about how that population is changing and how organisms that were born at the same time end up having to deal with different issues and have different life history patterns. So you can have dates of independence when you become mature. When does that happen? It's happening later and later and later now. People are staying home with their parents longer than they ever did before. Reproduction, when do people start having kids? I didn't have kids till I was in my 30s. And then people dying. How late are they dying? So are you expected to die in the 70s, in your 80s, that kind of thing. And survivorship curves is a line graph that kind of emerges when ecologists plot all those different things together. All right, and you get these survivorship curves. You have three different types. So type 1, right, reflects high survivorship until late in life. So typically you have parents who provide lots of care. So this is us as humans. Typically, most of the time, is you provide lots of care of the young. So therefore, the young survive. You have very low infant mortality rates, and so the parents provide a lot of care and helping raise the offspring until they're mature. And so that typically keeps the death rate pretty high or pretty low, in making your age of death expectancy much higher and later in life. Type 2 is where you have a constant death rate at all ages. Typically, organisms are just as likely to be killed or die of disease at any age, so rarely reach maximum age, and so you just have a chance of dying from predators or some kind of death or disease or something that happens pretty much at a constant rate. So it doesn't matter if you're 2 years old or 80 years old or 25 years old. In this example, those organisms would all pretty much die at about the same rate. Type 3, you have a death rate is highest early in life. And so this is the organisms that produce lots and lots of babies, and most of those babies get weeded out. And so a lot of fish do this. So there's certain fish that produce literally millions of eggs. And out of those millions of eggs, 2 might actually make it to maturity. And so that's huge. But if you think about it, a fish, every time they reproduce, if 2 of them make it completely to adulthood, then as far as the population goes, the population is increasing pretty significantly there. So type 3 is all about producing lots and lots of offspring, but providing little or no care to those offspring and hoping that at least some of them make it. And so their survivorship curve is much, much different. So type 1, you get lots of survivors. Type 2 is pretty much a constant rate, and type 3, where you pretty much produce lots of offspring and hope that they do well. So this kind of shows the different curves that are involved for type 1, type 2, and type 3s. All right, natural selection. Traits that affect life history, traits like other characteristics can evolve. So these things that affect as far as how many offspring you make, how you take care of your offspring, how you survive, how you feed, all those different types of things can change and can evolve. So traits that affect life histories can be altered in a surprisingly short amount of time in response to selective pressures. So when the environment changes, these life history changes can actually change very, very quickly. In 2004, the human population growth rate was at 1.4, so over 1 billion people already confronted with limits to growth. Over 10 million die from starvation each year. And this is, luckily we've started dropping down below that one rate, so our population is decreasing, but now we're at 7 billion, so that's a lot. Growth rates were slow until about 10,000 years ago, so it took a long time for our population to kind of increase. Humans develop the ability to live in new areas. Humans increase the carrying capacity of their current habitats, so we are one of the few organisms that can actually do that. We can actually increase the carrying capacity by starting to grow crops and by importing things and pulling in things from larger areas. And so we can increase the carrying capacity by providing and creating our own food sources. So humans have found ways around limiting factors that tend to restrain the population. This is what allows us to have places like Tokyo that have over 1 million people per square mile, which is crazy. Technology has allowed us to expand and survive in a huge array of different environments. Humans were established in most of the world by 40,000 years ago. Starting 11,000 years ago, many humans started developing agriculture and domestication, right? Overcoming those limiting factors, more dependable basis for life, obtaining more food more efficiently, smaller areas removed food as a limiting factor for many of those areas, and started making it so that our populations could grow a lot more than what it had been. So we started going from we started basically living this idea of the exponential unrestricted growth. Our population slowly increased, and then once we started overcoming these, our population just kept on skyrocketing to the point where we had no basic carrying capacity. Until 300 years ago, poor hygiene, malnutrition, and disease kept the death rates down. Think of the Black Plague coming through, right? So it kept, because of our lack of understanding of disease and how it passes along, our lack of sanitation, we basically pooped where we walked and didn't really try to get rid of our waste products. All of that stuff kept the population down. But sewage treatment, soap, antibiotics, and increases in technology helped humans to sidestep those factors that were the limiting factor at that point in time. So we'd overcome the food limiting factor, we'd overcome the water limiting factor, we'd overcome a lot of the other limiting factors, but disease was still keeping us down. And with sewage treatment, soaps, and all that types of things, we were able to then overcome that limiting factor. And so we hit this thing of total fertility rate. So it's the average number of children born to women of populations during their reproductive years. So currently, well, this is a little bit dated, a little bit below is 2.8, which is still way above the replacement rate of 2.1. So right now, to simply replace the population, the replacement rate is 2.1. So having 2.1 kids for every set of parents. Right now we have 2.8 kids for every set of parents. As far as the world over, I think we're a little bit further down now in 2016 than that. I think we're right around 2 or a little bit below. That's what gives us below that 1.0 ratio. I think or at least in the modern countries. I think maybe if you go into a lot of the low advanced areas like parts of Africa and Asia and parts of South America, you'll still have a much higher rate because a lot of those offspring and all of those organisms end up, or a lot of those people help out with the parents and help out with agriculture, and so it's a lot more important to have more kids. Now in more of the advanced areas, you're in first world countries, you don't have that need for having children anymore, and so our replacement or our current total fertility rate is much lower than in those other areas. Demographic transition model shows how human population's growth rates often correlate with 4 stages of economic growth. So this is what I was talking about. So pre-industrial stage, transitional stage, industrial, post-industrial. So we got 4 kind of levels of or stages of economic growth where a group of organisms are, where a group of humans are within this 4 stages. Kind of shows how they're going to do as far as their overall increase in population. All right. So if you look at the different rates, at the different types that we have here. So per 1,000 population, you have stage 1, right, has an organism that ends up, so this is stage 1 right here, has an organism where you have the populations are high. So this is where you're pre-industrial, so organisms rate per 1,000 population, so is high, and then the population actually ends up increasing very high. Stage 2 is where the death rate starts to drop. So stage 1, you have your death rate is very high, so lots of organisms are dying. The birth rate is very high, so you're making lots of kids. But your total population is kind of still wavering, because since you have a lot of people dying and a lot of people being born, your population kind of balances each other out. Once you move into stage 2, that death rate plummets. Right? You still are making lots of babies because you still have lots of agriculture, is very important, but the death rate is much, much lower. You got lots of food now, you start taking care of yourselves better, and so that population, since the death rate is decreasing and the birth rate is still pretty high, that population skyrockets. So this is the highest rate of growth. This is what happened in China in the 1960s and happened to us way before that. right? And then if you move into stage 3, which is industrial, that's when people stop having kids, right? So it's not quite as important to have all those children anymore. You don't need to have 8 kids in a family to help with the farm and help all the different things that the family needs to do to be able to survive. And the death rate drops really low at this point in time. And so you still have a pretty high increase because the birth rate is fairly high, but it slowly is dropping, right? So it kind of starts to level out. You kind of start seeing the population kind of balance out here in stage 3. And then finally in stage 4, post-industrial, so this is basically where the United States is, and Europe, and a lot of other places, is where you have the population is pretty high, but the birth rate and death rates are low, right? So you're not having a lot of people die, but you're not having a whole lot of offspring either. And so this is maintaining that population kind of around that rate. And this is where we are now. When you're maintaining that 1.0 replacement, or that replacement rate around 2.1, the population is no longer increasing anymore. You're getting people dying, but you're getting about the same number of people being born, and so the population kind of levels off, but it levels off at a pretty high rate, and that's the 7 billion people we have on the Earth today. So this is where a lot of the Earth is at right now, but we still have groups that are all the way down in stage 1, still working through stage 2, and then quite a few in stage 3. The idea is to try and bring these guys all up into stage 4, so that our population kind of starts to level off, and you can start to have with, at least as far as people in the stage 4 are concerned, we have a big issue with lots and lots of deaths, and so we try to impact those guys. But if we take out all these deaths, they still have all this birth rate here, and so the population will continue to increase. And so it's a tricky thing because not everybody wants to be in stage 4. A lot of people like to live in stage 1 and stage 2, but being in stage 4, we like to see that death rate a lot lower. So we start impacting these stage 1 to stage 2 people way before they're ready for it, and way before their economies and their societies are really prepared to having that death rate decrease so much and that birth rate still being high. And so the population in those areas will start to increase to the point where they can have some serious issues with food, with why you have a lot of starvation now in some areas, and overpopulations in areas beyond their limiting factors for that area, because we provide medical care to help keep these deaths down as far as disease and stuff, but we're not providing enough food and water for all the people that are now able to survive, and how fast that population is increasing on the stage 1 and stage 2 areas. So it's kind of a tricky thing that we have to deal with as far as understanding how populations grow and what you're actually and how you're impacting those areas like sub-Saharan Africa and places like that. When you're sending lots of medical aid, what kind of problems can that actually occur? I mean, it's good to save people's lives and give them medical aid, but then you're also causing that population to go beyond what some of the basic limiting factors of food and water are. And so that's when you have all the children starving, and so now we're having to send food over, and it's a big tough thing. So it's something that people don't really think about, especially when you just start giving lots of money over to certain organizations, but it's something that probably should at least be aware of. Not saying it's a bad thing, just saying be aware. So pre-industrial stage is before the technology and medical advances, so death and birth rates are very high, rate of growth is very low. All right, transitional stage is your food production and healthcare improves, so we got lots of agriculture. The death rate drops, but our birth rates stay pretty high because you got lots of agricultural families, big families provide lots of help in the field, and you get lots of so you get lots and lots of births, but much less deaths, and the population really starts to increase. Industrial stages, people move to cities, couples want small families, birth rate slows, medical care is optimized, so death rate stays very low. And then finally in the post-industrial stage, growth rates are negative, and that's where we're at right now in a lot of places. United States, in Europe, the growth rates are actually negative, and so our populations are slowly starting to decrease down to a more manageable level. Again, the key there is slowly, right? Our population is really not decreasing that fast, so there's not something to be worried about. It's actually probably a good thing. So future projections put many developing countries into the industrial age within the next couple of decades. So like I said, we still have a lot of areas that are in stage 1 and stage 2, but within the next 20, 30, 40 years, they project that most of those areas will be into that industrial age where people are moving into cities and out of those more rural areas. However, there are signs that the rapid growth, population growth could overwhelm the economic growth, trapping many of the countries in the transition stage. And this is where what I was talking about earlier. So we're having all this extra technology and input from stage 3 and stage 4 countries, into those stage 1 and stage 2 countries, but by doing this, it actually ends up trapping them within that transition stage, within that lower area stage, because you're keeping them, allowing the people to live in the farmlands and in the more dispersed areas by providing them the food and the nutrients without them actually making the technological advances to move up to the next levels. And so it causes some issues as far as how those populations are going and whether and how they can actually take care of themselves. Having a zero growth rate might sound ideal. However, it takes a large workforce to provide for individuals in a higher age bracket. So that's where, that's where we're running into some issues now, especially if you start thinking about Social Security. What they pretty much tell me is that I won't have any when I get to that age. I get to pay into it my entire life, and then it'll pretty much be minimized to nothing. By having so it takes a large workforce to keep the older people alive, and if you keep the older people alive for longer periods of time, when they're out of that workforce, so let's say you retire at 65, people are living to 80, that's 15 years that all the people below have to provide support for those people. And so that takes a lot of effort. How many hardships are you willing to endure for your parents or your grandparents? How much will your children endure for you? So you complain about taxes, you complain about all these different things, but that's what's one of the reasons why a lot of the Social Security and things are keeping on going up is because we have this larger group of older individuals that we have to take care of now. And so, that's the general idea. So, do you want to keep taking care of them, or do you not? And so, are you prepared to make that sacrifice, or what's going to happen to you? Because it's actually going to probably be most of us where it really comes into crunch time. Most of our parents actually are pretty okay. It's going to be most of us that are actually going to have. It's going to be our children making the decisions on how we're going to be. And so, it'll be interesting to see how that turns out. All right. So take a look over the notes and let me know if you have any questions.